Good afternoon, everyone. This is Christine Friedenreich speaking. I'm the Associate Scientific Director for the O'Brien Institute for Public Health at the University of Calgary, and it's my great pleasure to be your moderator for today's session that we are co-hosting with the Department of Community Health Sciences. I would like to begin by acknowledging the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Kainai, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wellesley First Nations. We also want to acknowledge that the City of Calgary is home to the Métis Nation of Alberta, Region 3. For today's session, I just want to start off with a few housekeeping reminders. For attendees, we will be having a Q&A session at the end of our seminar today. So please just ask your questions via Q&A box that you have at the bottom of your screen. You can also email your questions to iph@ucalgary.ca following the session. I would also like to point out that we've already received some questions to our email address, and we will try to answer those questions in addition to the ones that we've already received in the Q&A. I also want to say that this webinar is being recorded and it will be posted to the O'Brien Institute's website following the event. In addition, I also want to mention that we will also be trying to answer any questions that have not been answered during the Q&A session, and that we will post those answers on our website. So I'll begin now with the introduction of our presenters. It's my great pleasure to be able to introduce Dr. John Connolly. He's a professor and former head of the Department of Medicine at the University of Calgary and Alberta Health Services. He's an infectious disease specialist with medical training who's held several leadership roles with the Canadian Infectious Disease Society, the Canadian Committee on Antibiotic Resistance, the Canadian Expert Drug Advisory Committee, CIHR's Institute of Infection and Immunities Institute Advisory Board, and the WHO's Advisory Group on Integrated Surveillance of Antimicrobial Resistance. He's currently the chair of the WHO's Infection Prevention and Control Research and Development Expert Group on COVID19 and a member of the Canadian Expert Advisory Group on Antimicrobial Resistance. He's received many career awards in areas of research, teaching, service, including the Ronald Christie Award for Contributions to Academic Medicine in Canada, the Medal for Distinguished Service from the Alberta Medical Association, and last but not least, the Order of Canada. He's an active consultant in clinical infectious diseases with current research interests focused on antimicrobial resistance and stewardship, prevention of hospital-acquired infections, and novel innovations in healthcare. Our next speaker to introduce is Dr. David Fisman. He's a professor of epidemiology at the University of Toronto and a fellow of CIHR's College of Reviewers. He's a physician epidemiologist with research interests that fall at the intersection of applied epidemiology, mathematical modeling, and applied health economics. He completed a residency in internal medicine at McGill University and Brown University before completing a fellowship at the Beth Israel Deaconess Medical Center in Boston and an MPH at Harvard School of Public Health. He is an AHRQ fellow in health policy at Harvard Center for Risk Analysis and has held faculty appointments at McMaster University, Princeton, and Drexel Universities. He develops and applies novel methods that allow physicians and public health experts make the best possible decisions around communicable disease control using the best available data, and has been a recipient of CIHR funding for the study of COVID-19 epidemiology. And our final speaker, or will actually be our first speaker, is Dr. Kim Prather. She's a professor and distinguished chair in atmospheric chemistry at Scripps Institution of Oceanography at UC San Diego. She's the founding director of the NSF Center for Aerosol Impacts on Chemistry of the Environment. She's published over 220 papers detailing how aerosols influence the atmosphere, climate, and human health. She holds several patents on innovative technologies for measuring atmospheric aerosols, including an aircraft-based aerosol time of flight mass spectrometer instrument that has been flown through clouds to study how different aerosol sources affect clouds and precipitation processes. She's an elected member of the National Academy of Sciences, the National Academy of Engineering, and an elected fellow of the American Geophysical Union, the American Association for the Advancement of Science, and the American Academy of Arts and Sciences. So now I'll hand over the talk to Dr. Prather, who will begin the discussion, to be followed by Dr. Fissman, and finally with Dr. Conley, and then we'll have the Q&A. Thank you very much.
Okay, well, thank you for that introduction. I just want to make sure I can share my screen. Is it sharing? I think it should be up there now. Okay, can everybody see my screen?
Yes,
okay.
That's perfect.
Thank you. All right, well, thank you. I'd first like to thank University of Calgary and the O'Brien Institute for organizing this discussion today. Since I'm starting, I thought I would just sort of remind everyone about what the topic that we were given to discuss is, and it's about that. But basically, we're discussing whether airborne transmission is an important and mitigatable aspect of the COVID-19 pandemic. And so what I'm going to start out with is presenting about the evidence that supports, yes, indeed, it is airborne transmission is, in fact, a predominant mode of transport. And I'll say up front that we're not, I'm not going to say that it's 100%, but it can be quite significant. And today I'll talk about why that is the case and why, and the evidence that supports that. And the answer to the mitigatable aspect is, yes, it is, once we all acknowledge that it is airborne. So this slide probably has the most importance of anything I'm going to talk about. I could spend the whole 10 minutes on this, but basically this is kind of a artist's rendition of the view of sort of how people produce aerosols and droplets. And this is actually based, I'm an aerosol scientist by training, this is based on physical measurements. And so, basically what we see here is that when people are just simply, singing, talking, breathing, they're aerosol producers. And that's something that's become a big, obvious part of this pandemic. And I'll talk more about that. In other words, they don't have to be coughing and sneezing. They don't have to have symptoms. And so one of the major ways this virus has snuck its way around the globe is that it can be largely spread by people who don't know they're sick. So they're not coughing and singing or sneezing. They're just out in the public talking to people. And so basically what happens is, you produce, when you speak louder, you produce more, but when you speak, you produce aerosols. Little tiny aerosols that come out, lots of those, thousands of those come out of your mouth continuously while you're talking. And those will float in the air. And if you're indoors, they can float in the air. They can go much further than 6 feet, or basically they can build up in the room, just like, think about cigarette smoke. They basically are of that size and they behave visually very similarly. You also produce some number of, very few, I would say, when you're speaking, you produce many fewer large drops. And this is defined, I'm going to talk about bigger than 100 microns, because these follow a very different aerodynamic pathway. And you can see it in this figure. They basically are immediately falling to the ground, and they will fall to the ground, most of them, within 6 feet. If you're unlucky and you're standing too close, these could hit your eyes, nose, or mouth. But basically, as you can just see from this picture, and this is the thing that I will talk a lot about, that the greatest chance you have of being infected by this virus is inhaling this virus at close distance. So let me just go through the pathways. You can do short range inhalation just based on pure number, based on physical measurements. This is the most likely pathway. Long range, it becomes more important, but it's much more dilute. And so this is what the public health community has referred to as airborne, but I'm just going to call it long range inhalation because that's more related to how we can fix it. And then there's the droplet spray, and this is not, above 100 microns is not going to be inhaled, as I already mentioned. And so aerosols float and droplets drop. All right, so what is the evidence that we have? Well, basically, let me start with the public health community has pushed or said that you don't get aerosols unless you're doing, and we don't protect against aerosols unless you're doing aerosol generating medical procedures. And one of the big things that's come out of this massive amount of research that has been done, which I'm trying to capture, as I mentioned, in 10 minutes, is that this basically people are aerosol generating people, AGPs. And so, and more importantly, I think a big part, as I say, the way this virus has stealthily made its way around is you produce aerosols all the time, but you're more infectious and you're producing potentially more aerosols before you have any symptoms, without any symptoms. And so this has been shown in a number of ways, and I think it's something we've come to really appreciate, and the evidence on this is just growing and growing over time. So you get short range inhalation, as I mentioned. So then the question became, do we see it in the air? And the answer is yes. It's really, really hard to sample viruses from the air because there's so few, and you sort of destroy them when you sample them unless you use special methods. And that was used by Lednicki to sample these viruses in a very delicate way so that you can actually culture them from air. So we've checked, I think, all the boxes, on the fact that this virus definitely can be airborne. There's also long-range inhalation, and that leads me into my next slide. So the main pathways, like I say, I'm going to sort of support the airborne aspect of this. And the biggest piece of evidence that we have are these thousands of super spreader events. And they all take into account, indoors, low ventilation, no poor mask use, long durations of exposure in crowds where people are talking, yelling, and singing and not wearing masks. So you know what those areas are. So there's many examples of gym outbreaks. There's choir practice. There's a famous choir practice that we've all heard about. There's also restaurants, and this just came out within the last week. This is just showing one infected person in a restaurant. They've modeled all the dynamics. They measured the flows, and they found out that there was a pocket of air that was trapped at this end of the restaurant. So all 3 families at this end of the restaurant got sick. There was video that showed they never interacted or never came within 6 feet of each. A lot of them didn't come within 6 feet of each other. So this is a great example of what happens in an indoor environment. One that just came out in the CDC EID journal is this one, which is basically an outbreak at a big church where a chorist turned out he was sick, sang 3 days, infected people over 2. So he sat here 10 feet above the crowd, and these people were more than 50 feet away from him, and they all became infected just in this one part of this massive church, which turned out it didn't have hardly any ventilation. People weren't wearing masks. They used video to show that the chorus never interacted with the people, so there's no contact. There's no droplets either because the chorus had his back to the people that got infected. So droplets don't shoot out and then turn around and go back. So this is a great example of something where airborne has to be invoked. And finally, sometimes some of these real world situations are difficult to sort out through the epidemiology because there's so many factors. So then there's these animal studies where you can they put ferrets in cages, they pushed air. Basically this little guy was infected, and there's 4 90-degree bends. Droplets don't do bends. And so only aerosols can make it all the way up. And in fact, the one on the top got infected. Again, another example of no contact, and it's not droplets. So what about these AGMPs? So there's a paper that just came out by Wilson et al., and this is an adapted figure from that. And basically what you see is the number of aerosols that are produced by a particular respiratory activity versus just breathing. And you see there's an enhancement from talking. There's more if you're exercising. There's more if you're shouting. There's even more if you're coughing, up to 371 times more than if you're just breathing. Compare that to AGMPs. You can see right away where the conundrum lies. There's barely any AGMPs that are coming out during the things where people are, in this case, being offered and told to wear N95 masks. They're saying use airborne precautions. In the case where the aerosols are actually coming out and it actually is airborne, many of them are being given mostly surgical masks. And so the number of reports of people being infected with these surgical masks is just taking off, unfortunately. And so, basically this is something that needs to be addressed, and we hope it will be soon. All right, so I hear this all the time, droplets versus aerosols. Why do you care? You just want to say aerosols because you're an aerosol scientist. That's not it. Basically, why does acknowledging airborne matter? It matters because the things that we put in place for droplet precautions, both in terms of masks as well as controls to clean the air, they do not fully protect us or anyone against aerosol transmission. So let's think back to July. We wrote a letter, many of us, 239 experts wrote a letter to WHO saying it's airborne, please acknowledge that it's airborne. And at that time, WHO came back with a scientific brief, which said, this is just a few of the things that they were asking for. If we're going to say aerosols are coming out, we need to prove that it's coming from people. That has been shown over and over. If we're going to say that airborne is important, we need to show that it's viable, not just in the air, but it has to be viable. This hasn't even been still shown for measles. In fact, has been cultured from air. And healthcare workers aren't really showing up as getting infected. Well, that is now being shown, and in many recent papers, it's becoming more and more concerning, is what I will say. So WHO also mentioned that they monitor the emerging evidence, and they'll update the brief. And so far, that hasn't happened yet, but I'm still hopeful that it will soon. So once we acknowledge that it's airborne, we can fix it. That has been the frustrating part to me. Basically we can shift. This was back in July again. There was a lot, saying that surfaces it's just theater. It just makes you feel good to wipe down surfaces, but it's not fixing what we really should be cleaning, which is the air. So CDC just came out this week with a statement that the chance of getting infected through contact with a surface is very small. In fact, it's less than 1 in 10,000 touches of a contaminated surface that you will get sick. They have also been coming out with, CDC has been coming out with many more reports, and you can see that these viruses can remain suspended in the air for minutes to hours. They've been shown to remain infectious for hours, and airborne transmission is something that CDC is now acknowledging we need to address. So it's really, really important. It's great that CDC has done this, but this is a global pandemic, and we really need the WHO to clearly acknowledge that it's airborne. Why? Because, well, the good news is WHO came out with a great video a while back on ventilation, that it's so, that's what we should be doing. And I was really happy to see that, but it doesn't tell people why. And social choices are better if people understand why they're being asked to do what they're being asked to do. So why does ventilation and filtration matter? It reduces the aerosols, it cleans the air. Why do we care about how good our mask fits? Why do face shields and plexiglass barriers not work for aerosols? They're designed for droplets. Why should we not be going to bars and restaurants where there are no masks being worn? So a lot of this we knew over 100 years ago. A lot of this we knew from other places. So the point is, I truly believe, that we can end this pandemic once airborne is fully acknowledged globally. And the bottom line, the proof of that is that places that have acknowledged it's airborne have fared much better. This just shows the European Union cases and the United States cases versus, where we haven't embraced airborne, versus places like Japan, South Korea, Taiwan, and Vietnam, where they did. And the cases are almost, you can't really detect very many. So we can look at what I question is, why can't we just look at lessons learned from other people, lessons learned from over 100 years ago, that ventilation matters. The guidance on how to clean the air, I truly believe, will allow all businesses and schools open, and this time stay open. And I will just say there's a cadre of us that have been helping individual businesses. Lindsay Marr, who many of you know, helped a gym, which is notoriously high risk. Her gym has not had a single case because they just cleaned the air. I've helped schools, I've helped businesses, I've helped restaurants, but we can't do it one-on-one like this. This has to be, we should share this information globally, and we're limited in our capacity to do that. And so also the other thing we need to get out is, once it's airborne, we can protect people. We can protect healthcare workers, frontline workers. And this is really, really important. So I'm going to stop in a second. I just want to mention, we just had a paper. Trish Greenhalgh was the lead on this. It was just accepted at the Lancet. It'll come out next week. This is the top 10 scientific reasons, many of which I just covered, that it goes into, that show, this is it's getting to be an overwhelming amount of evidence from different directions, direct measurements, mechanistic measurements, models, epidemiology. Just look at the world. We're in the middle of a pandemic. Airborne has got to be factored in. So I will stop. I'm going to hand it off to David, but before I do, I just want to mention, the questions that I hope we can address based on what I just presented is, how do we explain, the great impacts we see? So many fewer infections outdoors versus indoors, and ventilation does such a great job. These massive number of outbreaks that we see, how can you explain, it's now acknowledged that the airborne long range inhalation is occurring, but how can it not be happening at short range where the concentrations are higher? And finally, I would love to hear from Dr. Conley. When will, what is it going to take WHO to acknowledge this evidence and that it's, predominantly airborne transmission that is leading us into this global pandemic? I'm going to hand it off to David now.
Thank you. I hope no one regards this as too sacrilegious. I'm presenting a bit of a conversion narrative, and I've got my Caravaggio picture here of St. Paul on the road to Damascus, because I'm a physician epidemiologist, and I have to say I have learned a ton over the past year of the pandemic about many things. One of those has been really discovering this amazing discipline of aerosol science, which I must say I was fairly clueless about. And what I'd like to describe is how learning about aerosol, learning about established aerosol science, has really helped me understand the pandemic differently, and how it's helped me to account for factors that were very difficult to explain early on in the pandemic. So this is a funny virus. I've referred to it before as Schrodinger's coronavirus, because it's such a study in contrasts. We've known for over a year now that there are a bunch of paradoxical features of SARS-CoV-2. These include presymptomatic transmission, which Kim's mentioned, extraordinary heterogeneity of severity, ranging from critical illness to asymptomatic infection, over dispersion of reproduction number, which I'll unpack a bit on the next slide, with the majority of new infections caused by a small minority of primary cases, something on the order of 10 to 20% of cases producing 80% of downstream infections. And lastly, the Japanese characterized this disease very early on as having sort of a signature, which is transmission occurred where the 3 C's were operative, where it was closed, close, and crowded. They ascribed that very early on to aerosol, and that led to some very interesting public health guidance. And I remember chuckling when the Japanese guidance around reopening of amusement parks included things like, you should scream inside your heart on the roller coaster, don't scream out loud. But that reflected an awareness of the importance of aerosol. And these are just some pictures to show you how relevant this concept of overdispersion is to SARS-CoV-2. Over here on the left, this is Kailan Sun's paper in, I think this was in Nature, looking at some Chinese contact tracing data from early in the pandemic. And what you can see here is that most cases do not transmit. Most cases have a reproduction number of 0. But what we see is that 80% of secondary cases come from only 10% of the cases. So we've got a lot of dead-end cases. If we have a disease like this is a graph from Adam Kucharski from Lancet. What we see is, I've likened this to sort of trying to start an old outboard motor, if any of you have had that experience, where you pull on the cord 6 or 7 times and it turns over on the 8th time. That's what we get with over-dispersed reproduction number. Most cases are dead ends, so we import cases, and boom, suddenly the epidemic explodes. That's exactly what we saw in Ontario, where we were importing cases from January to March, and our epidemic didn't start until March, likely with a missed super spreader event. You can see Adam's sort of plotted out probability of an epidemic based on number of introductions. I had 2 epiphanies, to continue with my inappropriate religious metaphor. Epiphany number 1 related to learning about Jack Schijven's work from the Netherlands in terms of how remarkably variable the amount of aerosol humans can generate is based on what they're doing with their respiratory tracts and their vocal cords, where we can go from 1 log or fewer aerosol droplets with quiet breathing, all the way up to 4 or 5 logs if we sneeze or cough. Schijven pointed out that with this variability in aerosol production, the setting in which the aerosol is produced would also be very important. If we're in crowded, poorly ventilated settings, more aerosol could be more impactful. So we're starting to see how we could have so much variability in transmission with this virus. If generation of aerosol is that variable, and the ability of aerosol to hang is that variable depending on environmental settings, then epiphany number 2 came from my colleagues Paul Chen and Frank Gu at University of Toronto. And there's a lot of information in this slide, and I don't think we have time to unpack it fully. But what I'll point out is that they found that the viral loads in individuals with SARS-CoV-2 are highly skewed. So most people have relatively low viral loads. You can see here that it varies by day of infection, but a small minority of individuals have very high viral loads. And this is a plot showing how many viral particles you would expect in aerosol droplets, in aerosols of different sizes, not aerosol droplets, at the 98th percentile versus the mean. So what this graph is saying in a nutshell is on average, people aren't infectious. However, a minority of individuals will be highly infectious. And I've started to refer to this as the Lemony-Snicket model of COVID transmission, where you need a series of unfortunate events. This is vocalization or coughing, singing in a poorly ventilated indoor setting by an individual who's on the high end for viral load in order to create these super spreader events. So then the reproduction number we observed for SARS-CoV-2, which is around 2 to 3, the basic reproduction number, we can now understand as a weighted average of cases who have a personal reproduction number less than 1, which is the majority, and cases that have a massively high aerosol generated reproduction number, which is the small minority. And again, Kim has already said this, that allows us to focus our efforts. We can focus on ventilation, dedensification, bidirectional protection from masks, and appropriate use of respirators for those at greatest risk. And then we transform an epidemic into a controllable and preventable disease. And I had the same idea as Kim did to just show Canada versus Japan as a study in contrast. And I'll end it there, and I hope I've done okay with time.
That's perfect. Thank you very much, Dr. Visman. So now I'll invite Dr. Conley to share his screen, and we'll have his presentation.
Thanks very much. I'm going to thank the organizers for the session and thank the co-presenters. I'm going to look at the evidence supporting droplet contact, oral fecal vertical transmission. I will touch on the issues pertaining to aerosol transmission as well. Just by way of disclosures, which I think is important to be able to do, I hold several grants from CIHR, several of which are related to COVID, also from AHS, EDT, Alberta government, and the WHO. I'm on a number of advisory committees, including for the province of Alberta, PHAC, the WHO, and advisory board for the Institute of Infection Immunity for CIHR, and also a member of the Cochrane Collaboration Respiratory Virus Working Group. I advise these groups. I do not reflect the views of the Public Health Agency of Canada or the WHO. Let's just be very clear on that, but I do provide advice to them, as do many other individuals. So my objectives, and they were laid out, I won't spend time on this, is to assess sorting the message, looking at the evidence for transmission. And the first thing I'll just mention about sorting the message is that we have social media in total overdrive. This is the first time in history that we've had instant social messaging. We get preprints published without peer review. They're picked up by Twitter streamers who often can look at the science. It can be misinterpreted. We've seen many peer-reviewed journals with retractions. Think of the high-profile New England Journal and Lancet retractions. We've also had many reports now about the science and how the pace is fast, first, and frenetic. We're seeing many short reports and commentaries and really opinions and what I consider rampant pandemic exceptionalism. So just as a fair warning, be careful, critically appraise all the papers you look at and use some common sense in looking at this literature. Very important to use those critical appraisal skills. Here's an example that many epidemiologists are now using as the classic epidemiologic fallacy. I use it in my teaching now. This is the study that came out in the June of 2020, looking at the New York data where they showed the day after they went to face coverings, there was a reduction in the number of cases. Many epidemiologists from around the world wrote in about this, where they declared that airborne transmission was the dominant route of transmission based on this paper. And they could have had 5,000 epidemiologists rather than the number that wrote in. It's quite a fallacy to suggest that the day after you do something, there's an immediate reduction in the number of cases. This was called for as a retraction with PNAS, and the New York Times also discovered that these individuals had chosen a couple of friends through some old PNAS Academy rules to allow the peer review to go through very rapidly. So just a word of warning to beware. So let's just go back to some very basic principles about exposure to a microbe. And then not all exposures lead to transmission and invasive infection. This is fundamental infectious diseases epidemiology. You've got a colonized or infected source, and then you've got ability to be able to have a susceptible host. You've got the avidity of the host receptors, the inoculum, the viability, very important, and the virulence of the microbe. And then you have to look at the effectiveness of the hygiene and the controls. And just to remind you about the routes of transmission and the way we teach in infection control and public health, which is important. We've got animal vectors. They can be influenced by wind, water, abiotic, environmental factors. Then we talk about contact, which is direct and indirect. Direct is through close contact. Think of sexually transmitted diseases, for example. Indirect is through fomites, where things are deposited on the environment. And then move to the host. Then we have the droplets in the airborne, with some debate about the size of the droplets and the aerosol creation. And then finally, fecal oral. And we know many examples there, norovirus, which has plagued cruise ships for many years, for example, or salmonella, or many other types of diseases. When we talk about modes of transmission of respiratory viruses, we talk about droplet contact, fecal oral, and airborne. And in all likelihood, they all come into play in this setting. And the greatest debate is the droplet and airborne. From the standpoint of setting about guidelines and guidance, we often talk about large droplets, small droplets, aerosols. So we use 10 to 100 micrometers. Those are generally heavier and fall. And then we talk about those that are finer, that can get into the air and be carried over long distances. And I think the other presenter had touched on this. It's important to remember that there's considerable overlap with respect to droplet size, and some very, very important principles that one needs to consider. And that's that in all likelihood, we see from the human airway a variety of sizes, from coughing, sneezing, talking, medical procedures, and then situational settings as well. And we're in all likelihood looking at a continuum from very large droplets to fine aerosols. Very important to look at that in terms of the situational, or what we call opportunistic settings, because there are things that can change this. And when you look at the biology of viable presence of virus, bacteria, or other pathogens, it's very important to take into consideration the very, very complex environment. And it's not a one size fits all. We have variability in the particle size, the distance, the propulsion. Think of a neonate versus an adult if they have cough, and how much propulsion you're going to get, the concentration, the settling velocity, the direction of the airflow, the number of air changes, temperature, relative humidity, crowding. It's very, very complex. And then last but not least, one has to look at the presence of a virus, if it may be present in the air or in fine aerosols. And then core virologists in basic science will tell you, you have to look at, is it replication competent? Is it infection competent? And you can split those two out. Replication and infection competent is what one is looking at from that regard. So let's look very quickly at, where do you find this virus? There have been many studies done, and I'll just touch on a few of them. Bronchoalveolar lavage, endotracheal secretion, sputum we know has a lot of virus. We know swabs do from the nasopharynx or pharyngeal, saliva. Most studies suggest that most of the viable virus is gone by day 7 to 8 in immunocompetent hosts. And we know that viable virus does not correlate well with RT-PCR. It does not also correlate with genome copies. Part of the reason is that you have a lot of genomes and RNA that hangs out for long periods, and you get mixed dead and live virus. There are now 3 studies that suggest cultivatable virus in stool, 1 in urine, and there's been transmission of those samples through a stool or urine to ferrets. There's now a study out from Calgary that's going to be presented within the next month, Dr. Joseph Vialuncal and colleagues, demonstrating cultivatable virus infection and replication competent in the placenta. And then in air samples, to date, there have been no replication and infection competent virus in clinical scenarios that have been demonstrated. We do see artificial laboratory-based settings with powerful jet nebulizers, which can produce aerosols. Here's a study from the Canadian National Microbiology Laboratory, just one of several that have been published around the world, looking at cultivatable virus, and it shows by about day 7, you can see in the red bars the majority of the virus which is present, and then measuring virus with TCID50, tissue culture infectious disease 50%, which if used a Poisson distribution can be relayed over into plaque forming units per ml, which I like to deal with. And this study showed, as it did many others, that after a week, we see a pretty rapid decline. And there are other studies, which I don't have time to show, that show the rise of the neutralizing antibodies. There are immunocompromised hosts who can carry virus longer. So if we look at the evidence to support droplet contact, it's consistent with high loads of replication and infection competent virus in things such as saliva. It's consistent with the transmission with SARS-CoV-1 and MERS-CoV. Overcrowding and suboptimal control of visitors were major factors in transmission of MERS-CoV, to take us back in time. And then if we look at secondary attack rates, in general, the WHO-China joint mission showed a range of about 3 to 10%. Multiple systematic reviews since have shown household mean rates of about 18%, non-household pooled rates of about 4%. We see higher rates consistently in several studies of symptomatic to asymptomatic individuals. We also see a lot of heterogeneity, and you have to be careful not to draw conclusions that there was a choir or the Diamond Princess or a chalet where a number of people became infected. There may be extenuating circumstances that are occurring in that setting. There may be mixed modes of transmission. So very important to look at this in the context of the totality of the evidence and the totality of the modes of transmission that may occur. We also see the RO consistently in the range of droplet contact viruses. Here, just to show you measles at around 15, varicella virus just under 10. And then here's the smattering of SARS and influenza, the common cold virus, and a number of others in terms of that rate. We also know that conjunctival penetration or touches in the macaque studies that have been done, you deposit a small amount of SARS-CoV live virus, it runs down the lacrimal duct, and then they present with a pneumonic illness. There are systematic reviews to show that the presence of goggles or shields can reduce that. We've also seen in Calgary, in 5,500 continuous person hours, 0 healthcare worker transmissions using standard surgical masks, gloves, gowns, goggles, or shields. We've since had some hospital-acquired transmission events in our healthcare workers, but when we've done anonymous surveys, we found, in fact, they are not following the guidelines and recommendations. So we think we have an explanation for that. This has been replicated in other settings as well, notably in Hong Kong. We've also had other studies that have suggested that systematic review recently with N95 respirators versus surgical masks, review of all RCTs with which I was involved with the Cochrane collaboration, there was no difference in the transmission of respiratory viruses. This is predominantly influenza, but also human coronavirus was contained within that review. There are no studies, although there is one going on now led by Dr. Mark Loeb, which is a very important randomized controlled trial. And here's a study from almost 100 patients now, collaboration with the Lee Cushing Virology Institute, University of Alberta. We've been studying patients. I've seen personally 140 COVID patients. I use only a medical mask as part of my precautions, and I consider it to be quite adequate. And we've been studying for the last year, gathering patients. I've probably collected 75% of these myself personally, interviewed many of these patients, and have a very firm bedside understanding of this illness. With respect to sputum and ETT, 10 to the 6th, many people said you'll never see that in a patient. We see it routinely. 10 to the 5th plaque forming units per ml. Remember, each plaque contains 100 to 10 to 100 infectious virions. So if you got 10 to the 6th, that's 1 million. If you multiply that by 100, you have 100 million infectious particles. That is a massive amount of virus. We see it in saliva. We've seen it in cough bags at 10 to the third plaque forming units per ml. Hand washing specimens, we're able to find it. Nasal prongs lying on the beds. Dr. David Evans, who was the virologist running the level 3, suggested we do KISS specimens because of the frequency of a double peck on the cheek. We find it in KISS specimens. We found cell phones, bed rails, tissues, face cloths, dentures, toilet seats containing replication and infection contaminated virus. We have done a series of specimens with singing and talk bag specimens. We have not found a single one to date. We've done both inpatients and outpatients. The mean is very important. Some studies have said you can't find cultivatable virus. We find this virus quite easy to cultivate. You need fresh viral cells. You need sometimes to use Temperus 2, which is a protease capable type of virus or a cell culture as well. We found hand samples of the cough bags we've done. We found a third of cough bags are positive. I've done them at the bedside. You see bits of spittle fly into it. Continuous speech. We've not found a single presence of cultivatable virus. We've done hand transfer experiments because it's difficult to get human challenge in the bedrooms or in the rooms of these patients where the left hand is cleaned, the right hand is then shakes the left hand, and we see equivalent amounts of virus transfer. We've also found tissues. One we found left for 9 hours at a bedside, dentures left for 4 hours, and we easily find cultivatable virus in this setting. Here's the virus here. You can see it on the plate, the courtesy of Dr. Lin and Evans from the Li Ka-shing Virology Institute. And to be able to show that this is true virus, it's been spiked with anti-S protein, and you can see it lights up like a Christmas tree. And this is a placenta where we found a virus in the mother, the child, and the placenta growing at 10 to the 2 plaque forming units per ml. We are the first group in the world to confirm vertical transmission, and whole genome sequencing shows that they are identical strains. Here's an example of a Kleenex found, 2.2 times 10 to the 4th, hand transfer experiment showing equivalent transfer. Here's dried spittle that we left dry for about 2 to 3 hours, and you can see absolutely no decay in the amount of virus that's present. Here's a published a paper we've just had in March showing in a transplant patient at the day 30, cultivatable virus in cough specimens, a KISS specimen. The cell phone was loaded with cultivatable replication and infection competent virus. Another face cloth I just pulled off the bed of a patient showing huge amounts of virus. Very interesting paper about a dose response curve. The work with the Rocky Mountain NIH just south of us. We often have them up to our Banff conference on infectious diseases. They're showing a 3-fold increase in the binding capacity of this particular virus, SARS-CoV-2, compared to MERS and SARS-CoV-1. And interestingly, I don't have time to walk through all of this, but regardless of the inoculum, there's no inoculum effect with the severity of disease in a hamster model. Once you're infected, and it just rises up from there. Human challenge experiments, just to take you back to the common cold studies from the MRC Cold Research Unit, they were able to find with alpha coronavirus as little as 4 PFUs per mil can cause infection. And there are now human challenge experiments going on. I've just had colleagues from the UK indicate we know that this virus can be carried on many substances. It was thought maybe this is only with laboratory strains. We've actually shown it in clinical strains as well. And some recent studies from Public Health England showing the presence on multiple electronic equipments in school children. And then just to remind you with rhinovirus that 50% attack rate with the famous coffee cup experiment where rhinovirus was picked up from fomites. We fully expect we're going to see this. We have been able to demonstrate fomite transmission through to a hamster model, thus fulfilling Koch's postulates. This work suggests that we have fulfilled not only Koch's postulates, Bradford Hill, the Gwaltney and Hendley postulates for virus transmission, and also the Bird and Segre genetic sequencing postulates, and those of Fredericks and Relman. So to just the last couple of slides on aerosol transmission, absolutely it's possible. We've seen that with the Amoy Gardens. We've seen it in these crowded settings, which have been discussed, but pretty low poppy numbers. And to date, looking at those studies very carefully, it's been very difficult to be able to find a viable virus in this setting. There's one study that was done to show situational. This was in a barracks back in 1970, studies done in the late 60s, where they put giant fans in a military barracks and shown that you can have the transmission of aerosolized Coxsackie A21. So there are now several systematic reviews.
Don, sorry,
yeah.
I'm just gonna, we need to wrap up to get to the questions.
One slide, thanks.
Okay.
They ran overtime, so I guess I get to as well, just to be fair and equitable. They cut into my time, so.
That's okay.
Several systematic reviews to show with the University of Oxford, and they're well worth a look. There's 2 more that are coming up as well, and they're living reviews. So my personal assessment, why is this virus so contagious? It's very hardy in the environment, very high titers. The environment is literally saturated with this virus. We have frequent human behavior. I believe that there's pretty good evidence that a fomite transmission occurs. There's good evidence that droplet occurs. And I think it's important to look at, there's no absolutes in the science of the biology of transmission. We need to look very carefully. It remains to be seen in my mind that airborne is the predominant when we've got all this cultivatable virus activity. Certainly it can occur. We have questions that we need to answer, not hypothesis generating, but hypothesis testing. And with that, I'll close. Thanks for your time.
Okay, thank you very much. I'll ask all the panelists to return. I've got one first question that I would like to ask for all of the panelists. And thank you very much for your presentations. I would just want to ask if you could please address the question essentially of what is the difference then between indoor and outdoor super spreader events? How do the 2 sides explain the different transmission hypotheses that would explain what's happening between indoor and outdoor super spreader events? Okay, go ahead, David. Unmute yourself first.
Happy to take that. I keep it short. And the major difference between indoor and outdoor super spreader events is indoor super spreader events are abundant. There are thousands of them. There's a systematic review in JID from about a month and a half ago that was able to identify a grand total of 5 published instances of outdoor transmission, one of which was a one-on-one conversation outside in Wuhan. So we have several orders of magnitude more evidence for outdoor than indoor, which directly supports aerosol transmission, because outdoors what we do have is ventilation, but the force of gravity is the same indoors and outdoors. We don't have different gravity indoors and outdoors. So that's a very, very strong argument in favor of dominant aerosol transmission.
Kim, would you like to address that as well?
I think he said it really well. I mean, that is the main, I would say, smoking gun of this particular pandemic. And I would love to hear Dr. Conley, how he would explain them if he doesn't include airborne.
Yeah, I think I've denied that airborne transmission can occur. It may be, as I said, situational, and we do see situations and circumstances where it can occur. It'd be interesting to be able to look at outdoor settings. There have been some outdoor settings with super spreading events as well. When you look at some of these soccer and football games, and after we looked at the Blue Jays and the Texas Rangers, let's see what happens with that outdoor event to be able to see as well. So it may not be the be all and end all. We do know that there are certain situations, and absolutely, if you think you're at the seaside and you get sea spray and the wind picks up, you can feel this salt spray on your face. You can sometimes taste it as well. So we absolutely know there are situational airborne settings, but to be able to say that it is the only and predominant means, I think we need better scientific evidence, and to look at the totality of the evidence, and to also look at mixed modes of.
Can I just comment really quick on that? I just want to clarify, I hope I didn't. I don't think I said it's the only. I think that the ratios change depending on settings. I do think it's predominant overall, especially indoors, especially in the super spreader events. And so I just want to make sure that I was clear on not trying to say that it's only. But to me, if it is something and it is contributing to a global pandemic and people are are getting infected and dying, then it should be addressed. We should protect those people, is my main feeling.
Okay, fair enough. I'll go on to another question. So this question was submitted before the seminar. The question is whether some of the new variants of concern tend to need less time to transmit. This question comes from one of our viewers from Europe, and they said, in many places, we've said someone is a contact person if they've been around someone who's infected for at least 15 minutes. Should criteria like that be changed, also for other reasons, and communicated? Go ahead, David.
I'm happy to take that. I think the arbitrariness of 15 minutes was sort of shown to be problematic before the variants had emerged in force. And I think our best source of data on that actually comes from the NFL, from the American Professional Football Leagues, where you've got some very, very deep-pocketed individuals doing what it takes and paying what it takes to keep a group of highly paid athletes safe. So a lot of testing, a lot of environmental control, a lot of care around masks. And they had a joint publication a couple months ago with CDC pointing out that they were having transmissions in under 15 minutes of exposure from people who are well more than 6 feet apart, strongly implying aerosol. And that was their take home from that joint publication, is the gaps relate to aerosol. So I think that's a pre-variant. We can talk about variants in a subsequent question, but I think that 15-minute guideline was problematic even before the variants emerged.
Anybody else want to respond to that question, John?
Yeah, I'll respond. I think, as I mentioned, I think it's important to look at the totality of the evidence and use both epidemiologic evidence, basic science evidence, which I think is extremely important. And I would like to see more basic science in some of the aerosol studies that have been done, because we need to be able to try to understand all of this, certainly from the standpoint of some of the transfection studies they've done, and with this NIH group looking at the binding and the avidity. One needs to start to look at the P1 and the 1351 and the B117 variant. There are changes that are occurring. It's quite possible that they bind much more avidly. So it may take a very small amount of virus, and if you've got a very low minimal infectious dose, it may take very little contact, a quick handshake, and then somebody touches their mouth. You can have transmission in 10 seconds. It wouldn't take necessarily 15 minutes to be able to do.
Okay, so I have another question here. This question is the question about the Chinese CDC in early February 2020 had an early warning that SARS-CoV-2 appears to be airborne, and there were many early case studies from elsewhere. And the question is, why did Canadian public health leaders either shut down this hypothesis, or they were very slow to acknowledge that aerosols could be a major source of spread? The question here is, at the very least, why haven't the precautionary principles been applied from day one? Who would like to take that? Go ahead, David.
I can't answer that question because I think that's astounding. I have no answer to that question. I have the same question.
John, do you want to take a hit?
No, I think they had recommendations that were looking at the modes of transmission of respiratory viruses. And, it's this entire debate that we're going through today to be able to look at, what is the predominant mode of transmission? Where do we get situational airborne? I don't think anyone's denying airborne transmission, but to be able to come out and say it is the major and predominant mode of transmission, from my perspective, I would like to see a much higher level of scientific evidence, and including some basic science to be able to see that this is indeed the case and where it might be occurring and what would need to be done. And certainly from our experience in Alberta and in the phase 1, we were using standard recommendations from the Public Health Agency Canada with gowns, gloves, medical masks, and as I said, the 132 patients and over 5,500, that's almost 8 months of continuous contact time with highly infectious, hot viral patients and not a single healthcare worker transmission. So I think there's good justification for those recommendations. They work for us.
Go ahead. So, I mean, there are lots of questions coming through. We have over 100 questions here, and so I won't be able to ask you all of them. But there seem to be a lot of people are wondering about what kind of advice we should be giving to the general public right now about the level of masking, particularly for, let's say, in schools, for healthcare workers, what level of precaution should be recommended.
You know, I just want to follow up in terms of, I think we have to separate out the science from the supply chain. And I think those two things have really gotten conflated through the past year and a half, where there's been a desire to not have this be aerosol generated because we didn't have the N95 masks. And I think both in Canada and the US, I think that's really problematic. I think you get, you slide off, evidence-based decision-making and fall into some decision-based evidence-making when your principal concern is an inadequate supply chain. That's gone away now. Both sides of the border, we are now manufacturing N95s in Ontario. And I think it's time to let the science speak. And I think it's time to listen to the precautionary principle. I think Dr. Conley's acknowledging that aerosol is a mode of transmission, unless I've misheard. And if that is the case, we can get all rabbinical and go back and forth about what fraction is aerosol. But it's pretty clear that there are infections resulting from aerosol transmission. And now that we have the supplies in terms of N95 masks, we need to start treating this for what it is, which is a dominantly aerosol transmitted disease.
Yeah, I would completely disagree with you, Dr. Fissman. And I think there are many side effects, and I would remind you that anytime you look at benefits, you need to look at harms, of which there are many harms with N95. And I think to ignore them, you're at your peril. There's acne, there's also issues with eczema, conjunctivitis, CO2 retention. There's been decreased O2 concentrations in pregnant women, many side effects to this. And I think one needs to look at harms as well as benefits anytime that you think that you're going to do this. And there's also importance to be able to look at the fact that from the standpoint of what we're doing now and the public health recommendations, if there is good compliance, in general, these recommendations do tend to have benefits. And one needs to be able to weigh the totality of the risks and the benefits together before coming up with a recommendation that all persons should be wearing an N95 respirator.
Can I quickly on that, please? Yeah. When you talk about harms, I totally disagree. And I think people who've lost family members and been sick themselves and healthcare workers would disagree with you too. Because harm of acne versus death or long COVID, we've lost 133 million people have gotten this, and nearly 3 million have died. And so harm versus catching COVID, wearing a good mask, I would endorse it completely.
Yeah, I'll just respond by saying that in SARS-1, there are many cases of individuals wearing N95s who did acquire SARS-CoV-1. So one has to look at issues of droplet, contact transmission, fomite, and you have to look at the totality of the recommendations that would come into play in this setting.
We lived with SARS-1, it was a different disease.
And also, it was different, and it's also, you're conflating the two, and that, yeah, there's other ways to get it. Nobody's saying that, but right now we're protecting against all those other ways, and we're not protecting against airborne properly. That is a problem.
I think this has been an outstanding discussion and definitely some counterpoints that we've got clearly presented here. We have over 150 questions that have not been answered. So what we will do is we will save all of these questions. We will send them to our speakers. We will get them to answer the questions. And if there are differing points of view, we'll make sure that we record both of those, because I think there's these topics are very, very important. And we really acknowledge that there's been a lot of interest in this topic. And we want to thank the audience for participating in today's seminar. I would like to very much thank our speakers for your very excellent presentations and lively discussions that we had. I wish we had a whole other hour to go through all of the discussions, and perhaps we will pick up this topic again, because I think there's lots and lots to be discussed, and we're not out of the woods yet with this pandemic. So thank you so much for your time, and thank you very much to the speakers for your wonderful presentations.
Thank you.
Thank you.
Bye now.